All right, welcome to the Explainer. Today we're going to pull back the curtain on a concept that's, well, it's pretty much everywhere. It's powering some of your favorite apps, but you never even see it. We're talking about the linked list. So, you ever wonder how your music app can just shuffle songs so easily, or how your browser's back button just works? Well, believe it or not, the answer is this really elegant idea we're going to get into. The magic behind Shuffle, your browser history, even that life-saving undo button. Yeah, it often boils down to this one super clever data structure. Okay, so to really get why linked lists are such a big deal, we've got to talk about the thing they were designed to fix. We need to look at what came before and, what its problems were. Let's talk about the array. It's a data structure you've probably run into before. So here's the deal with arrays. They're kind of rigid. Their size is fixed from the get-go. So let's say you want to add something right in the middle. You literally have to shift every single thing after it down one spot. What a pain. And deleting an item? Yep, same problem, but in reverse. You got to shift everything back up. It's just slow, it's clunky. What we really need is something more flexible, right? Something dynamic that can grow and shrink on the fly, where we can pop things in and out without all that drama. And that is where our hero of the day comes in, the linked list. It was literally invented to solve exactly these problems. It's a whole new way of thinking about how to chain pieces of data together. Okay, so what's the big difference? Here it is. An array stores everything neatly, side by side in your computer's memory. A linked list? Nah, its pieces can be scattered all over the place. So how do they stay in order? Well, that's the secret sauce, a clever system of pointers. So the basic building block of a linked list is something called a node. Just think of it as a little two-part package. The first part is your data, the actual thing you want to store, like a song title or whatever. The second part is the pointer. And all that is an address that basically says, hey, the next piece of the chain is over there. A few analogies really help here. Think of a train. Each train car is a node, and that little connector between them, that's the pointer. You can add a car or remove a car without having to rebuild the entire train, right? Or think about a music playlist. Each song just points to the next one in the sequence. That's really the core idea we're talking about. Okay, so we get the what. But how does it actually do that magic trick? How does it handle those insertions and deletions that are such a headache for arrays? Let's get into the nitty-gritty. Check out how simple this is. If you want to add a new item to the very front of the list, it's just 3 quick steps. 1, you make your new node. 2, you tell that new node, hey, your next item is whatever the old first item was. And 3, you just say, okay, new guy, you're the official start of the list now. We call that the head. That's it. It's ridiculously fast because you're not shuffling any other data at all. And deleting from the front? It's even easier. Seriously, all you do is take that head pointer that's pointing to the first item and you just move it over to point to the second item instead. Boom, done. The old first item is just floating out there, totally disconnected. It's gone. Again, super, super fast. No shifting. So this table really breaks it down. Adding or deleting from the beginning, that's what we call O of 1, or constant time. That's a fancy way of saying it takes the same tiny amount of time whether your list has 10 items or 10 million. It's instant. But, and this is a big but, here's the trade-off. What if you want to find an item somewhere in the middle, or add one to the very end? Well, you have to start at the beginning and walk through every single node to get there. That's O of n, or linear time. The time it takes gets bigger the more items you have. Okay, I know this might all sound a little abstract, a bit computer science-y, but I promise you, you are using linked lists every single day. You just don't know it. Let's look at where this thing is the unsung hero behind the scenes. Okay, check this out. Your browser's back and forward buttons, that's actually a special kind of linked list, a doubly linked list, where every page knows about the one before and the one after. So cool. Music playlist, of course, that's a perfect example. The undo/redo feature in your apps, that's just a linked list of all the actions you've taken, letting you step back and forth through time. Heck, even your computer's operating system is using linked lists under the hood to manage memory. They're everywhere. Now, as amazing as linked lists are, it's super important to know they're not a silver bullet. They're not the perfect tool for every single job. You gotta know their strengths and weaknesses, when to use them, and when to grab something else from the toolbox. So when should you reach for a linked list? For sure, when your data is changing a lot, growing, shrinking all over the place. If you're constantly adding and removing things from the beginning of a collection, like a stack of tasks to do, a linked list is absolutely your best friend. It's the most efficient choice.
And big one here, if you have no clue how big your list is going to get, a linked list is a lifesaver because it can just grow as much as you need.
But on the flip side, they're a terrible choice if you need to jump straight to a specific element. Like if you need to get the 500th item. With an array, that's instant. With a linked list, you gotta start at the beginning and follow the chain 499 times to get there. Not great. Plus, all those pointers take up a little extra memory, and since the data's scattered around, it's not always the most efficient for your computer's memory cache. And this might be the most important thing to take away from all this. Really getting the linked list, this simple idea of a node pointing to another node, it's absolutely fundamental. It's like learning your scales before you can play a symphony. This concept is the key that unlocks way more advanced, powerful structures like graphs and trees. So, in the end, it all boils down to this: a simple chain of data and pointers. That's it. An idea that completely smashes the rigidity of arrays and just blows the doors wide open to a whole new universe of programming possibilities. So the real question is, now that you know how it works, what are you going to build with it?